I'm going to start with briefly talk about what is supercomputing, and then talk quite a bit about an overview of the Exceed resources that are available, with keeping in mind what is relevant for computational economics. Okay? And then I'll talk briefly about how to access and use Exceed resources. There is actually a lot of detail in the slides, but I'll probably skip over some of them, but I'll make the slides available through Mao, and of course there's much more details and help available if you actually want to get onto one of these Exceed resources. Okay, so what is a supercomputer? You might have seen pictures of that. Some of you have actually used it and are experts on them, but that's maybe how one looks like. So it is essentially a bunch of commodity computing components plus some enhancements. So so you can consider a supercomputer to be made up of a large number of so-called nodes. Each node you can think of as just a laptop or a workstation. In fact, if you just bought a brand new workstation in your lab yesterday, it might be actually faster than a node of, let's say, the Bridges supercomputer at PSC, which was obtained 2 years before. But there's many and many of them in the supercomputer. And then what's new, what you probably wouldn't have, is that these large number of nodes are connected by a very fast interconnect for very efficient data movement between these different nodes. So in your home, the kind of data connection you might have is Ethernet. This is way faster than Ethernet. So that's one of the new things that a supercomputer has that you probably don't have. And then the other thing is a very fast parallel large file system for reading and writing lots and lots of data. So those are the two new additional things that a supercomputer often has that you may not have. And talking then about a few different flavors of supercomputing, the one that has existed for a while is high performance computing, or HPC, which typically means you are running a single application across many processors in a very tightly coupled way. The other one is high throughput computing, where you are kind of running smaller applications, but running many of them at once. One instance that is very common maybe in economics as well as engineering, which is my background, is just doing parameter sweeps. So high throughput computing requires a little less data movement because each of these applications is smaller, and but high performance computing is where you have a single application running across many nodes. You have to do a lot of work to make the data movement efficient, so that the processing elements are fed data at a high rate, and that might require a lot of work. Then fairly recently, what has become very important is also data intensive computing, where basically the ratio of data to computing is much larger than what used to be before. And that requires more focus on data movement and data storage, particularly input-output operations per second. Okay, so since this workshop is about data-intensive computing and big data, I'm going to focus a little bit more on that. So again, this is a fairly new field of supercomputing. It was brought on by a data deluge from large numbers of sensors that have been deployed recently, as well as large-scale genomics, gene sequencing, and large telescopes in astronomy and things like that. Now, in some situations, there may have been a lot of data, but people didn't think of using them because it was just impractical, and as you have said, but now you can do that more and more. The strategies here again is actually going from hard disk, spinning hard disk drives to solid state drives, where the input-output operations are much faster, as well as file systems in memory. So in RAM, you can create file systems in RAM, and that increases the input-output operations per second quite a bit. And then there are software solutions for doing data analysis in very large-scale distributed fashion. For example, the MapReduce algorithm that came out of Google, of which Hadoop is an open implementation. And then there is another implementation called Spark, which is different from, it's just very efficient data analytics. And Hadoop and Spark, for example, often work together to really speed up data analytics. One of the examples here is in information retrieval, so that's Watson. When Watson won the Jeopardy in 2012, that was a big leap in machines efficiently retrieving information from a large database of information. A subset of big data is machine learning, which has become really, really important currently. And so machine learning is not just doing simple data analytics, but actually using data to improve its performance towards some task, such as image recognition, for example, or prediction of market prices based on historical information, time series information. So the emphasis again now comes back here to flops, because in machine learning you have to train a model to do the job properly using data, and you do that. So you do the training with data. So there's still lots and lots of data involved, but the training itself requires now lots more computations. So there's still a lot of data, but computations again become important compared to data. And for these kinds of computations, actually accelerators such as GPUs and FPGAs do a very good job, because a lot of them are sort of matrix operations, and you can really optimize them well on GPUs, for example. But then you still have to deal with a lot of data for the training, and so solid state drives and memory drives also help. Okay. As to algorithms for machine learning, so there's two categories in my mind. One is traditional machine learning, where, for example, the algorithms could be regression, all kinds of regression, linear logistic, lesser range, as Mao has mentioned. Then there's other things such as support vector machines, decision trees, and random forests, and they can look into nonlinear interactions in data and things like that. As to software, very popular software is scikit-learn, where a lot of these algorithms are implemented already, and that's Python based. Then there's also Apache Spark MLlib, and that can actually work with Python or Java or Scala programs. There's MATLAB has the statistics and machine learning toolbox. I think a lot of people here use MATLAB, so that's another good place to look for algorithms already implemented. There is a Java implementation called Baker 3. There's several others. And then, so these are the traditional machine learning tools and algorithms. They work usually well with low dimension, low size data. I mean, relatively low dimension, low size data. And then if you have very high dimensional data, such as images where each pixel may be a dimension, right? And very large number of them, there currently deep learning or new techniques involving neural networks have really started doing very, very well there. So it was around the middle of this last decade where deep learning methods came into being, and then they really did, the performance of these methods just took a big jump. So neural networks have been around for a while, but they were not doing that well compared to some of these other methods, and then deep learning came in. Deep learning essentially is many, many layers of neural networks, not a few, but several layers in a neural network. And they started doing really well towards the middle of this decade. Some very popular neural network configurations are convolutional neural networks, or CNNs, recurrent neural networks, generative adversarial neural networks, and so on. There are many open source frameworks for you to play around with neural networks. One of the most popular is TensorFlow from Google. Then there is a framework called Keras, which is actually a higher level framework that can sit on top of TensorFlow. Then there's other frameworks such as Caffe and Caffe2, Apache, MXNet, LBAN from Lawrence Livermore, and a few others. So on Exceed resources, a lot of these are already available, and several different versions. This is actually a very fast-moving field. So new versions come out pretty often, every few months, and we try. It's hard to keep up to date with that, but we try our best. Okay. So those were the different flavors of supercomputing that are current. And now let me talk a little bit about different programming paradigms for different parallel programming paradigms. So the first is distributed memory computing, and this has been there for a long time. This is really, I think, how parallel programming started. And basically, it's you have many processors, and each processor has its own memory, and it works on data in its memory. But processors may also need data that resides in other processors' memory. And if data is needed from another processor's memory, then that has to be explicitly requested and received from the other processor. Basically, the user has to put in explicit function calls in their code to actually do this data exchange. The way to do this is MPI, and you can do it very, very efficiently if you spend enough time, but it is hard. If you have a serial code and you want to parallelize with MPI, it might not be very easy in the beginning. So after a while, another parallel programming paradigm came along, which is shared memory parallel programming, also called symmetric multiprocessing, where every processor can now access all parts of the memory. So if I am a processor, I can and I want to compute on data here in memory or here, I can just grab that data and do some computation on it. For example, your laptop is a small shared memory machine, because all the cores in your laptop can access all of the RAM. Okay. The way to do this usually now is Openmp. And basically in Openmp, if you have a serial code, you can just put in so-called directives, Openmp directives, which are essentially just comments. And those comments serve as hints to the compiler to parallelize certain parts of the code, for example, a loop. Right? And so you can just take your serial code and stick in these comments, and then tell the compiler, okay, this is an Openmp code which has this Openmp directives or comments, and use those to create a parallel application, and the compiler will then do it for you. One important thing is that when you insert these comments, if you then compile in a serial fashion, it will still work, because then the compiler just treats those comments as, just ignores comments, right? So you cannot you still won't break your serial code if you stick in Openmp directories. So that makes things a lot easier. And a compiler then is doing a lot of the parallelization work for you. Then there's, of course, hybrids, which are combinations of distributed and shared memory programming, where you do shared memory within a node. A node, as I said, is a laptop, which you can think of as a small shared memory machine. And then as you go across nodes, you can do distributed memory. Again, a quick pros and cons of these two methods. So you can actually, because you have a lot of control over how you are parallelizing, exchanging data, with a lot of work, you can scale up to very high processor counts, 10,000 to 100,000 cores and even beyond. And MPI has been used for a long time, but basically the downside is that if you're new to parallel computing and you want to get your code to use large parallel systems, it is initially very hard to get there. There's a steep learning curve there, whereas in shared memory programming, you can actually get your code running in parallel pretty quickly by inserting these comments in your code, and the compiler will then do the rest of the work for you. But the amount of parallelism that you can get is limited. So around 100 cores is the limit. Beyond that, if you go from 100 to 200 cores, maybe you will not see a benefit from your shared memory programming. And then that's where hybrid comes in, where you can initially begin converting to a shared memory code, and then as you want to scale beyond one node, which is usually less than 100 cores, then you can, at that point, you can invest more time into distributed memory programming. Okay, then at the turn of the century, I think, another new kid came to town, which is accelerators. So the most popular accelerator now is graphics GPUs, graphics processing unit. They have been there for a long time for video processing, but around 2000 or so, they became also ubiquitous for general purpose scientific computing. And so they work well, really well for some certain kinds of problems. One of them is large-scale data computing, especially things like machine learning. They were initially a bit hard to program, for example, using NVIDIA's CUDA, but now there are software frameworks to make programming GPUs much easier. For example, OpenSCC, which is essentially like Openmp, where you stick in, again, directives, which are comments that the compiler can use to move parts of your code onto a GPU. Then there's something called field programmable gate arrays, or FPGAs, which have a lot of potential for amazing performance at low power. These are especially important for on-the-field computing, such as on robots, for example. So you might, for example, train a machine learning algorithm using GPUs on some supercomputer, but then once the model is trained, you can deploy it on FPGAs to do inferencing in the field. And because it's low power, so if it is deployed on mobile platforms like robots, that's really advantageous. So that was a quick overview of just supercomputing in general. I would say as a few takeaway messages is that a lot of people in computational finance use things like MATLAB or R, large shared memory systems that we have in Exceed. For example, share up to 12 terabytes of shared memory, and 352 cores at PSC. So MATLAB and R are very good candidates for these kinds of platforms. And then there's a lot of GPU resources on Exceed, and machine learning algorithms are a very good fit for that. There's also other things such as molecular dynamics, etc., that can make good use of GPUs. But from a data perspective, machine learning, if you're going to do machine learning, you should go for the GPU resources available on Exceed. Okay, so now a little bit more detail into Exceed. John Towns already gave a very nice short overview. It stands for Extreme Science and Engineering Discovery Environment. So it's an integrated set of leading-edge computational networking data software and, most importantly, support services to facilitate science. And by science, I mean not just the physical sciences, but social sciences, including economics, finance, things like that. People around the world actually use this. Most of the user community is US-based, but there's international users also. And they are using Exceed resources to improve our planet and the human condition. Funded by the National Science Foundation, and most importantly, it is free for all open research. For big allocations, you do have to spend some time writing a proposal to get access to the resources, which is only fair, but no dollars involved. Okay, it's already paid for by tax dollars. Here's a set of, so Exceed consists of many partners, some of which are resource providers. I think those are the ones that are important to you. They are the ones that host big machines, and then Exceed users can request time on those machines. The lead organization is the National Center for Supercomputing Applications at Illinois. John Towns is the PI of the project. He is at NCSA. And then I circle some of the big resource providers currently on Exceed. But then there's many other partners providing various other things such as management or training, etc. Who can access Exceed resources? So PIs of Exceed grants have to be researchers or educators at US academic nonprofit institutions. That includes postdocs, but not regular graduate students. However, if you're a graduate student who is an NSF fellow, you can also be a PI. If you're not, then you have to ask your advisor to apply for Exceed grant if you want to use the HPC resources in Exceed. Or you can ask a postdoc in your lab to do that, right? Additional users are the PI's collaborators, which could be foreign, outside of US, or their students, and they just need to be added to the PI's Exceed grant. So students, graduate students cannot, or undergrads cannot directly be PIs, but their advisors, if they are PIs, they can just add them to the grant. And I'll talk about that briefly in a few slides later. What resources are available? So there are compute resources. There are the special purpose resources such as GPUs. There's a lot of networking and storage resources. There are resources called science gateways, which are essentially web portals that allow people in a community to very easily do some computing by submitting some input and getting results. And the web portals, the science gateways, hide all the complexities that go behind actually running a code on a large resource, parallel resource, getting the data in, getting the data out, things like that. So within compute resources, there are massively parallel resources of the orders of hundreds of thousands of cores. And then there are large shared memory resources, for example, up to 12 terabytes at PSC's Bridges resource. There's high throughput computing resources such as the Open Science Grid and cloud computing resources at Indiana. There's several GPU resources available, for example, SDSC, PSC, Stanford. And each of these large computing resources also go with a lot of these parallel file systems or storage resources. Now, on some of these, I think on Tax Ranch at Texas, you can actually just request data resources to just store your data. At other places, you have to get both computing and storage. And then, last but not, but very important, is there are a lot of human resources. So if you are about to start using Exceed and you get a grant, but then you are not sure how to get your code to run on these Exceed resources, you can request something called Extended Collaborative Support Service, where somebody like me or Bob or some other person who has a lot of experience on these machines will work with you very closely to get your code running efficiently on one of these resources. And Bob will talk more about this in his talk. Okay, here's a quick snapshot of the different machines that are there. These are the compute resources, storage resources, and high throughput computing, which is OSG, and cloud resources, which is Jetstream at Illinois. You can actually go to that link up there to see that for yourself. And I believe you do not actually have to have an Exceed account to actually see this. Okay, and just a little bit more detail about the different data resources, since this is a big data workshop. So as John said, petabytes is now possible. There are multi-petabyte resources available. So that's kind of, you should kind of start thinking about that maybe. That kind of opens up the thought process to what might be possible, what kind of data sets you might now be able to analyze. Okay, so if you have these large big data resources, it's important to get data in and out of it. And there are several tools that are available on Exceed to do that efficiently and easily. There are command line tools such as SCP, GSI, SCP, and rsync. But then there's also this web-based tool called Globus Online, and that basically uses very fast grid FTP amongst different machines. So you can both move data between Exceed resources using these tools, as well as move data in and out from your system to the Exceed resources. What software is available? There's a lot of software available on the different supercomputers. A lot of them are open source, but there are also some commercial softwares available. For commercial softwares, the different supercomputing centers sometimes provide the licenses, but at other instances, you might have to bring your own license. But if you have any questions, or if there's some software that you want that may not currently be on one of these machines, you can just talk to us, and we install new software all the time. The link there, if you go there, it will take you to the comprehensive software search page, where you can actually type in the software you need, and you can see which resources in Exceed have that software. So if you're thinking of applying for a new grant to Exceed and you've never used Exceed before, and you're wondering, okay, do I have the software somewhere? That's where you would go to take a look. But again, if it is not there, please talk to us, and we install software all the time. Some of the software that is important for computational finance or computational economics, such as MATLAB, R, Python, those are probably more popular in this community, and they are actually, I think, pretty ubiquitous. I think most of the resources, or all the resources, have these, including packages under Python, for example, such as SciPy, NumPy, a whole bunch of machine learning packages. They are now available on all the different resources. If you're a little bit more adventurous, you might get up to C, C++, Fortran, together with MPI and Openmp, as you've mentioned. Those are, of course, those have always been there, of course. Now, there's some new things, such as VMs and containers. So That will allow you to, for example, just maybe take a snapshot of your laptop or workstation and put it onto a supercomputer. So you do not have to leave the familiar confines of your laptop environment. You can just take it to the supercomputer and use it. Okay. So here's a look at the web page for software, so for comprehensive software search. So you can basically type in a software, and as I said, MATLAB is available on almost all of the resources over there. I think R would be similar. And then I think you can click on them and you can see what versions are available for each of them. So that's a nice tool. So quick comment. So that's about the different resources that are available. Quick comment. So if you're going to use, if you're going to run on Exceed resources, you want to run in parallel, which you may or may not already be doing locally. And since the two common software tools that this community may be using are MATLAB and Parallel, MATLAB and R, I just have a slide on each for the different ways you can do that in MATLAB and R. So you can do job level parallelism. You can have a serial MATLAB code, and then you can have a script run many instances of that, one on each core, okay, using some script. And that's job level parallelism. You don't have to really touch your MATLAB code at all there. In MATLAB, you have inherently multi-threaded functions. So a lot of the matrix operations are just inherently multi-threaded. If you just launch it on, for example, your 4-core laptop, it will by default try to run those functions on all of the cores of your laptop. A way to control this is there's something called maxnum comthads in MATLAB, where you can control this behavior. The default is to just use all the cores that MATLAB sees. That can give you quite a bit of parallelism without you really doing anything. Just run it on a multi-core system and that'll happen. Okay, then if you want to be a little bit more adventurous, and then you can maybe think of either the Parallel Computing Toolbox or MDCS, MATLAB Distributed Computing Server. And within each of these, there are several ways you can parallelize your code. The first one is called parfor, which is just parallelizing a construct to parallelize big loops. So instead of for, so if you have a big loop and you in your original code it was for something, you just change that for to parfor. And now if there are more cores available, then that loop will be parallelized across multiple cores without you doing anything else. There are certain restrictions for using parfor. For example, the order of execution of the different iterations must be independent and things like that. But it's pretty easy in general to just use parfor to parallelize your MATLAB code. Then there's something called SPMD, which is more MPI-like. Single program, multiple data. That's really kind of MATLAB's implementation of MPI, where you kind of control all the data movement. And in MATLAB, you can also do GPU-based computing with constructs such as GPU arrays. You can do all the same things in something called MDCS. The difference between Parallel Computing Toolbox and the Distributed Computing Server is that PCT has to stay within one node. However, we have some very large nodes in Exceed. For example, there are nodes with 352 cores and 12 terabytes of RAM on bridges. They're called the extreme shared memory nodes. And you can run MATLAB on that node across all the, PCT on all the 352 cores. So you can do a lot with PCT. And then but if you want to go across nodes, then you have to use MDCS. SDSC, for example, has MDCS. And then you can just basically the same code, but now you can use multiple nodes and run your code across multiple nodes. Okay, using R in parallel. So again, the ideas are pretty similar to MATLAB. There's inherent threaded code that you can use. For example, you can just compile your R code, the R installation with an MKL library with threading turned on, and that will just parallelize those functions that use MKL, that make calls to MKL functions. MKL is math kernel library from Intel. There's PNMath, which uses basically OpenMP versions of standard math libraries, which are already parallelized with OpenMP. And so if you're making calls to those functions from those libraries, those will be parallelized. Then you can do distributed parallel computing yourself in R, including both multi-core and distributed and MPI-like parallelization with RMPI. And there's also this for each construct, which is similar to the par4 construct for parallelizing loops. Okay, so I want to then give some examples. So one great example, of course, of a great success in computation and finance with large resources is Mao's work. You already heard a lot about that, and then Bob will talk a little bit more detail in his talk about, because he worked closely with Mao on that using ECSS. Here's another example that was recently done on bridges, and that uses machine learning. And so this project was about looking at the security and uncertain quality, looking at the economic impacts of images and natural language in e-commerce, specifically looking at the impact verified photos, high-quality photos, can have on Airbnb business. So this was done on bridges, and the PI was at Carnegie Mellon Stepper School of Business. And in the project, 17,000 properties were analyzed for 4 months. 4 months data for 17,000 Airbnb properties were analyzed using bridges GPU nodes, using computer vision algorithms. And so the findings were that, so first of all, rooms with verified photos were booked 9% more often. And then after separating the effects of photo verification from photo quality and room reviews, it was found that high quality photos, just being high quality, results in 2,500 of additional yearly earnings for those properties. So these might make sense, but this study kind of did some quantitative analysis of the effects of having high quality verified photos on Airbnb business. And interestingly, they found some spillover effects, such as on the neighborhood level, if there's a lot of rooms in a certain neighborhood that have verified high quality photos, then in general that neighborhood gets a lot of business. So anyway, this wouldn't have been possible easily without machine learning applied on GPU nodes in Exceed. Okay. So then I will very quickly go over how to get allocations. Again, we already talked about who can get allocations, and then you can go to something called the Exceed user portal to actually request an allocation, which is a web-based portal not just for requesting access, but also managing your grant, getting help, and things like that. Here's how the Exceed portal looks like. There's the portal.exceed.org is the address for that. So basically, if you are new, you can just create an account. Anybody can create an account. My mom can create an account. But then if you want to actually use the Exceed resources, you have to have your account added to some grant that has already been approved. So not anybody can actually use the Exceed resources. Okay, so here's the sign-in. And then once you sign in, you will see something like this, where there are lots of tabs. The two important tabs are My Exceed and Allocations. My Exceed is where you manage your existing allocation or grant. Allocations is where you request or renew your grant. And then there are some other very important tabs like Training, and help and documentation. Okay, so basically if you go to allocations and then go to submit review requests, that will take you to where you submit your allocation. And there are different kinds of allocations you can request. If you are about to start on Exceed, the thing you need to do is request a startup allocation. And that will give you a fairly up to 200,000 service units, for example, which equates to, for example, 22 years of computing on a single core. So anyway, it's a significant amount. And it might take just about half an hour to request that. For bigger allocations, you have to do something called XRAC. But for that, you must first have a startup allocation and then have explored how you're going to run your code on one of these large resources and use that information to then go for an XRAC account. That requires a little bit more effort. It's a proper proposal, but that can get you millions of service units. If you are thinking of just teaching a course using one of these big resources, you can request an educational allocation. And you don't have to have a startup to go for educational. You can just directly go for educational allocations. I'll talk about campus champions a little later. Okay, so again, you can just go to startup allocations. We have already talked about a little bit about who can request, and I mentioned how much you can get, quite a significant amount, through a startup allocation up to 200,000 service units. A service unit used to be core hour. Think of core hours as service units. Okay, and then this is how you request a service unit. Basically, you need to fill out a form with some basic information. You need a title and an abstract. And then you need your CV, and then you just need to upload all of that information through this web tool and click submit, and you will get probably the allocation within 1 to 2 weeks. So it's fairly easy. It's probably half an hour on your part, and then wait of a week or two, and then you would get it. Here are the different resources that you can request. For compute resources, you need to specify service units. Again, think of core hours. But now that there are other kinds of resources, such as GPU, for GPU resources, it's actually GPU hours. Or for large memory resources, it's terabyte hours. And when you click on one of them, it will explain what the SU means for that particular compute resource. Okay? You can also ask for storage resources in gigabytes and advanced services such as human expertise to help you run your code. And that's just a yes, no, and that's pretty much it. So here's, for example, so if you wanted to request all the different parts of bridges, there's regular memory, GPU, large memory, and storage. You click on them, and then you have to enter how much you want on each of them. And here's the explanation of what one service unit means on bridges large, on GPU, on regular memory. So it's all very nice and explanatory. And I already mentioned you'll get it in 2 weeks, within 2 weeks. And I mentioned this. So a startup can get you up to 22 years on a single core. Or more importantly, now that you have these big resources, you can now start thinking about how your research can expand, given that now you have you can start experimenting with that. That's the more important part. Okay, adding users, again, the users should just, such as your students, they can just go on the Exceed portal and create their own accounts and then tell you their username, and then you have to just add them to your grant through the web portal. If students are done, you can go to the web portal and remove them from your grant. So all that management you can do yourself through the web portal. Or you can actually assign a grant manager who can do it on your behalf, like a postdoc, for example, or a PhD student who is going to be there for a while. Okay, and then if you go again on the Exceed portal, clicking on accounts, it will show all the machines where you have accounts. I have accounts on all of the resources. And each resource has a local username. It will also appear here. So if you want to directly connect to the machine, you will need the local username. Connecting to the machine, again, you can connect directly through an SSH client from your, such as PuTTY. But for that, you need to know the local username, which you can get from the web portal shown on the previous slide. And then you also need a local password, which you can sometimes set. For example, at PSC, you can just go to this website. APR stands for Automatic Password Reset, to set up your initial local password. Or if you forget it, you can reset it. And for some other resource providers, you have to email them and ask them for a password, or contact them to ask them for a password. The other way is single sign-on. So that's this. So you can go to the web portal, and from there, using two-factor authentication now, you can sign on to different Exceed resources. So you can go through the web portal to the different machines, or you can just do directly. Running jobs on Exceed, you can run it in batch mode or interactive mode. I'll kind of quickly flip through this, but you can. I'm around. You can ask me for more details or later through email. While running, since this is big data, it's important to know about different file systems that are available. Some are small and permanent, some are big and permanent, or big and temporary. And then, as I said, you can run your code in batch mode, where you submit your job, go away, the job will run some time, and then you come back and get the results. You have to write a little script. Usually, this is an example for writing a script to do this batch processing. You can also do things interactively, which might be actually exciting for this, or useful for this community to know. So you can just get onto a compute node and then just typing commands and seeing results, and just working interactively. Okay, this is a way to manage software environments on Exceed called modules. I won't go into the details right now. There's a lot of ways to get help. Again, I'm going to share these slides with Mao. Bob will talk next about extended collaborative support services in quite a bit of detail. Now, on the Exceed portal, there's a lot of training that Exceed does. Okay, so if you do not know about MPI and want to learn, there's workshops on MPI or Openmp or GPU programming. And you can actually go to the training tab and get a calendar of the upcoming training events. And there's a lot of online training also that you can participate in. So that's an important thing to remember. Yes?
I want to emphasize on this point
okay.
in particular. You can get this for free.
Right.
Up to close to half of the folks that participate in training offered through Exceed do not have allocations on our systems. So if you have students that are coming up in your group and they need to learn these things, you don't have to have an allocation. You can send them here, you can create your account, you can sign up for training. There's online and in-person training. There's extensive training that we provide. And I want to make sure people understand that that part does not require you to buy any technical proposal.
Yeah, excellent point. Finally, there's something called campus champions. So they are faculty or staff at a particular institution, for example, with an interest in helping others in that institution start using Exceed resources. And so they receive specialized training from us at Exceed, and so and then they can transfer that knowledge to others in the institution. So you can find out whether there's a campus champion by going to the campus champion website, and then there's a current champions button and in there, and that will tell you whether there is a champion. Or if you're interested in becoming a campus champion, there's also a link to send a request for that. If you want to know more about that, get in touch with us and we can tell you more about that.